California's north coast experienced another significant reminder of its dynamic geological setting when a magnitude 5.6 earthquake struck near Redwood Valley in Mendocino County during the afternoon of June 24, 2026. The earthquake occurred approximately 7 miles or 11 kilometers north of Redwood Valley and originated at a depth of roughly 5.5 miles or 8.9 kilometers beneath the surface. Within hours, dozens of smaller earthquakes had already been recorded across the surrounding area, highlighting an active seismic sequence unfolding near one of Northern California's most important fault systems. Questions quickly emerged across the region. Was this a standalone earthquake or the beginning of a larger swarm? Why did the earthquake occur in this particular location? What does the concentration of aftershocks reveal about stress movement beneath Mendocino County? And what significance does the event carry for communities situated along one of California's major fault corridors? The answers lie within a landscape shaped by millions of years of tectonic motion. Northern California occupies one of the most geologically complex regions in North America, where multiple fault systems intersect and interact. The earthquake's epicenter places it near the Maacama Fault Zone, a major right lateral strike-slip fault extending through Mendocino County and passing close to Ukiah, Redwood Valley, and several smaller communities. Given the location of the seismic activity, the Maacama Fault Zone is widely regarded as the most likely source of the earthquake. Initial seismic measurements indicated a magnitude 5.6 event centered north of Redwood Valley at coordinates approximately 39.36, 2 degrees north latitude, and 123.229 degrees west longitude. Although moderate in magnitude by California standards, the earthquake was strong enough to be felt across a broad portion of Northern California. Residents reported shaking over a wide area, with effects extending well beyond Mendocino County. Magnitude 5.6 earthquakes occupy an important category within earthquake science. They are powerful enough to produce noticeable shaking across large regions and capable of causing localized structural damage, particularly in older buildings or structures not designed to modern seismic standards. At the same time, they remain substantially smaller than the largest earthquakes historically experienced in California. Mendocino County sits within a transition zone linking several major tectonic systems. The region exists near the northern extension of the San Andreas Fault network, where numerous parallel and branching faults accommodate the ongoing movement between the Pacific Plate and the North American Plate. The Maacama Fault Zone forms one of the principal structures within this network. Stretching for approximately 120 miles, or nearly 190 kilometers, the fault trends northwest-southeast through Northern California. Like the more widely recognized San Andreas Fault, the Maacama Fault is characterized primarily by horizontal movement. During an earthquake, one side of the fault slides laterally past the other, rather than moving predominantly upward or downward. This type of fault motion is known as right lateral strike-slip displacement. If an observer were standing on one side of the fault and looking across it, the opposite side would appear to move toward the right during fault motion. Over geological timescales, repeated episodes of this movement have gradually reshaped valleys, stream channels, ridges, and other landscape features throughout Mendocino County. Redwood Valley itself occupies a setting that reflects this tectonic history. Positioned north of Ukiah, the valley lies within terrain influenced by faulting, uplift, and erosion operating over millions of years. The surrounding mountains and valleys provide visible evidence of the forces that continue to shape the region today. Seismologists often pay close attention to earthquakes occurring on major fault zones because such events help reveal how stress is distributed within Earth's crust. Faults accumulate strain as tectonic plates continue moving. The rocks on either side may remain locked for years, decades, or centuries while stress gradually increases. When accumulated stress exceeds the strength of the rocks or friction holding the fault in place, a sudden rupture can occur, releasing energy in the form of seismic waves. Those seismic waves travel outward from the rupture zone in all directions. As they pass through the ground, buildings, roads, bridges, and other infrastructure experience motion. The intensity felt at the surface depends on several factors, including earthquake magnitude, depth, distance from the epicenter, local geology, and structural design. The Redwood Valley earthquake originated at a relatively shallow depth. Shallow earthquakes often produce stronger surface shaking than deeper events of similar magnitude because less energy is lost during travel through the crust. A depth of approximately 5.5 miles, or 8.9 kilometers, places the rupture well within the upper crust, where earthquakes frequently generate noticeable ground motion. Following the main shock, seismic monitoring networks recorded an expanding sequence of aftershocks. By early assessments, more than 60 earthquakes had already been cataloged. Such behavior is typical after a moderate earthquake. Aftershocks occur because the crust surrounding the rupture zone adjusts to changes in stress caused by the main event. An earthquake does not simply release energy at a single point. Instead, the rupture alters stress conditions across a broader area. Some sections of nearby faults experience reduced stress, while others encounter increased stress. The resulting adjustments often generate numerous smaller earthquakes over hours, days, weeks, or even months. The number of aftershocks alone does not necessarily indicate that a larger earthquake is imminent. Earthquake sequences frequently include dozens or hundreds of smaller events as the crust seeks a new equilibrium. Nevertheless, each aftershock contributes additional information regarding fault geometry and the distribution of stress within the affected region. Mapping the aftershocks provides valuable clues about the orientation of the rupture. Earthquakes occurring along a fault often produce clusters aligned with the fault's direction. As additional seismic data become available, scientists can compare aftershock patterns with known fault traces to refine understanding of which structure moved and how the rupture unfolded. The Maacama Fault Zone has long attracted scientific attention because of its potential to generate significant earthquakes. While it does not receive the same public attention as the San Andreas Fault, it remains a major component of California's plate boundary system. Geological evidence indicates that the fault has produced large earthquakes in the past and continues to accommodate tectonic motion today. Northern California's seismic landscape differs substantially from that of Southern California. Rather than being dominated by a single fault, many northern regions contain networks of interconnected structures sharing tectonic strain. This complexity creates a mosaic of earthquake sources capable of generating significant seismic events. The broader Mendocino region is particularly notable because of its proximity to the Mendocino Triple Junction, one of the most tectonically active areas in North America. A triple junction represents a location where three tectonic plate boundaries meet. In this case, interactions involving the Pacific Plate, North American Plate, and smaller tectonic elements create a highly dynamic environment characterized by frequent earthquakes and ongoing crustal deformation. Although the Redwood Valley earthquake appears most closely associated with the Maacama Fault Zone, the regional tectonic setting contributes to the accumulation and redistribution of stress. Movement occurring throughout Northern California ultimately influences neighboring faults, creating an interconnected system rather than isolated geological features. Historical records demonstrate that Mendocino County is no stranger to seismic activity. Numerous moderate earthquakes have occurred throughout the region during modern monitoring history. Larger events have also affected Northern California over the past century, producing varying levels of damage and reminding residents of the persistent earthquake hazard. Earthquake preparedness remains a central concern because even moderate earthquakes can expose vulnerabilities in infrastructure. Roads may experience cracking or localized slope failures. Utilities can be disrupted. Older masonry buildings often face elevated risk because rigid construction materials tend to perform poorly under seismic loading. One factor reducing potential damage from the Redwood Valley event was its location. Although communities exist throughout the area, the epicenter occurred outside major urban centers. Earthquake impacts depend not only on magnitude, but also on proximity to densely populated regions. A similar earthquake occurring directly beneath a large city would likely generate more significant consequences. Reports following the event focused largely on shaking intensity, localized inspections, and ongoing monitoring rather than widespread catastrophic damage. This distinction is important because public perception often associates any earthquake with severe destruction. In reality, earthquake outcomes vary enormously depending on location, depth, fault characteristics, and infrastructure resilience. Modern seismic networks provide far more detailed information than was available in previous generations. Hundreds of monitoring stations distributed throughout California continuously record ground motion. Data collected by these instruments enable rapid determination of earthquake location, magnitude, depth, and fault characteristics. Within minutes of the Redwood Valley earthquake, automated systems began calculating preliminary solutions. As additional observations arrived from stations across Northern California, researchers refined those estimates. This process explains why earthquake information sometimes changes slightly during the hours following an event. Earthquake magnitude itself represents a logarithmic measurement. Each increase of one whole magnitude unit corresponds to approximately 32 times more energy release. Consequently, a magnitude 6 earthquake releases dramatically more energy than a magnitude 5 earthquake, while a magnitude 7 event releases far more energy than a magnitude 6. A magnitude 5.6 earthquake therefore occupies a middle ground within California's seismic spectrum. It is substantial enough to command attention and generate extensive scientific analysis while remaining far below the most destructive earthquakes documented in the state's history. The physical process responsible for the earthquake began long before June 24th. Tectonic plates move continuously, though typically at rates measured in fractions of inches or centimeters per year. Over decades, these small motions accumulate substantial strain along fault systems. Eventually, stored energy reaches a threshold where rupture becomes unavoidable. During the earthquake itself, rupture propagated through a section of fault at speeds approaching several miles per second. Energy radiated outward through the crust as seismic waves. Different wave types traveled at different velocities, producing the characteristic shaking experienced by residents across the region. Primary waves, commonly called P waves, travel fastest and often arrive first. Secondary waves, or S waves, follow and typically generate stronger motion. Surface waves then move along Earth's exterior and can contribute significantly to shaking intensity, particularly at greater distances from the rupture. The interaction between seismic waves and local geology influences how shaking is experienced. Areas underlain by soft sediments may amplify earthquake motion compared with locations situated on solid bedrock. Valleys, basins, and filled ground can sometimes experience stronger shaking even when located similar distances from the epicenter. Redwood Valley and neighboring communities occupy a geological setting that includes both sedimentary deposits and more resistant rock formations. Such variability means earthquake effects can differ noticeably over relatively short distances. Another important consideration involves fault segmentation. Major faults rarely behave as single continuous structures. Instead, they consist of multiple segments separated by bends, stepovers, and other complexities. Understanding which segment ruptured during the Redwood Valley earthquake may help clarify the extent of stress transfer throughout the Maacama system. Researchers often compare modern earthquakes with geological evidence preserved in the landscape. Offset stream channels, displaced terraces, and fault scarps reveal the cumulative effects of repeated earthquakes over thousands of years. These records help estimate long-term fault behavior and recurrence intervals. Although no individual earthquake can determine when future earthquakes will occur, each event contributes valuable information regarding fault mechanics. The Redwood Valley earthquake adds another data point to the evolving understanding of seismic processes within Northern California. Infrastructure managers also examine earthquake sequences closely. Bridges, dams, pipelines, power systems, and transportation corridors may undergo inspections following moderate earthquakes, particularly when shaking affects broad regions. Even when no major damage is immediately apparent, evaluations help ensure long-term safety and reliability. California's extensive experience with earthquakes has led to some of the most advanced seismic building regulations in the world. Building codes have evolved significantly over time as lessons from past earthquakes revealed structural vulnerabilities. Modern construction techniques emphasize flexibility, energy dissipation, and resistance to collapse during strong shaking. The effectiveness of these measures becomes evident when comparing damage patterns across different eras. Structures built to contemporary standards generally perform better than many older buildings subjected to similar levels of shaking. Nonetheless, seismic risk remains an ongoing concern because not all infrastructure has been upgraded to modern requirements. Public awareness also plays an important role. Earthquakes provide little warning and occur without regard to weather conditions or time of day. Preparedness measures, emergency supplies, communication plans, and structural mitigation efforts all contribute to community resilience when seismic events occur. As the aftershock sequence continues, monitoring agencies will maintain close observation of the region. Statistical patterns suggest aftershocks will gradually decrease in frequency over time, though occasional larger aftershocks remain possible during the adjustment period. This progression is consistent with behavior observed after many moderate earthquakes worldwide. The earthquake serves as a reminder that California's geological forces remain active, regardless of periods of relative quiet. Decades can pass without a major earthquake affecting a particular area, yet tectonic motion continues uninterrupted beneath the surface. Stress accumulation and release represent fundamental aspects of the plate boundary environment shaping the western United States. For Mendocino County, the June 24th earthquake joins a long record of seismic activity, reflecting the region's position within one of Earth's most complex tectonic zones. The event highlights the significance of the Maacama Fault Zone, the importance of continuous monitoring, and the ongoing challenge of understanding fault behavior in a landscape defined by motion. One of the most closely watched questions following the Redwood Valley earthquake involves the possibility of dynamic triggering and whether the magnitude 5.6 event could influence stress conditions on neighboring faults throughout Northern California. The issue attracts attention whenever a moderate earthquake occurs near a major fault network because fault systems do not exist as isolated cracks in the crust. Instead, they form interconnected structures that continuously exchange stress across broad regions. Dynamic triggering refers to the process by which seismic waves from one earthquake travel through the crust and temporarily alter stress conditions on other faults, sometimes hundreds of miles or kilometers away. As those waves pass through surrounding rock, they can slightly increase or decrease the forces acting on nearby faults. In rare circumstances, this additional stress may be enough to initiate small earthquakes on faults that were already close to failure. The concept differs from static stress transfer. Static changes occur when the actual rupture permanently redistributes stress around the fault that slipped. Dynamic triggering, by contrast, involves the transient shaking generated by seismic waves as they radiate outward from the earthquake source. In the case of the Redwood Valley earthquake, attention naturally turns toward the broader Northern California fault network. The Maacama Fault Zone is not an isolated feature. It belongs to a family of major right lateral strike slip faults that collectively accommodate movement between the Pacific Plate and the North American Plate. Among these structures, the northern section of the San Andreas Fault remains one of the most scrutinized. The northern San Andreas extends from the Mendocino region southward past the San Francisco Bay Area. Portions of this fault last experienced major rupture during the historic earthquake of 1906. That event generated one of the most significant earthquakes in United States history, producing rupture across approximately 296 miles, or 476 kilometers, of fault length. Because more than a century has passed since that rupture, questions frequently arise regarding accumulated strain. Geological studies indicate that tectonic motion has continued throughout the intervening decades. As a result, portions of the northern San Andreas have gradually reloaded with stress. This does not mean the fault is necessarily about to rupture, but it does mean that stress accumulation remains an ongoing process. The Redwood Valley earthquake occurred within the same broad tectonic environment, yet distance and magnitude remain important considerations. A magnitude 5.6 earthquake releases a substantial amount of energy, but its ability to significantly alter stress on distant major faults is generally limited. Most static stress changes decrease rapidly with distance from the rupture zone. For the northern San Andreas Fault, located tens of miles or kilometers away, depending on the segment considered, the direct stress increase from a magnitude 5.6 earthquake would likely be relatively small compared with the immense tectonic forces that have accumulated over decades. The fault's long-term loading is driven primarily by continuous plate motion rather than individual moderate earthquakes. Nevertheless, scientists monitor these interactions carefully because earthquake systems occasionally behave in unexpected ways. Small stress changes can sometimes affect faults already near critical conditions. Earthquake triggering does not require a massive increase in force. In some situations, only a slight adjustment may influence the timing of an earthquake that was already approaching failure. The challenge is that no instrument can directly determine how close a fault is to rupturing. Researchers can estimate strain accumulation, analyze fault slip rates, and examine historical behavior, but the precise state of stress deep underground remains uncertain. Consequently, determining whether a specific earthquake has meaningfully advanced or delayed a future rupture remains extraordinarily difficult. The Maacama Fault itself may actually represent the area most affected by the June 24th earthquake. Aftershock patterns suggest that stress adjustments are concentrated near the rupture zone. Additional small earthquakes along adjacent portions of the Maacama system would not be surprising as the crust continues responding to the redistribution of forces. Other nearby structures, including segments of the Rogers Creek Fault, the Hayward Fault, and portions of the northern San Andreas system, will undoubtedly be examined for subtle changes in seismic activity. However, history shows that most moderate earthquakes do not immediately trigger major ruptures on neighboring large faults. More commonly, they generate localized aftershock sequences that gradually diminish over time. For now, the Redwood Valley earthquake serves as a reminder that Northern California's fault network operates as a connected system. The event highlights the continual exchange of stress occurring beneath the region while reinforcing an important reality. Every earthquake slightly reshapes the stress landscape, yet determining whether that reshaping will ultimately influence a larger fault remains one of the most challenging questions in earthquake science.